So now what happened that we would have non-parametric and parametric survival distribution. So Lagrange test and Gahan test is useful. So while you are preliminary making the survival curve comparisons and to understand better idea about that. But sometimes what happened that I have seen that curves look like different and it's become sometimes quite complicated to get an answers and to understand that which therapy is doing better, because in chemo or in oncology setups, whatever the way you are doing to make, so these always with as compared to the existing therapy, it makes always the neck to neck comparison. So and to neck having the comparison, unless and until you are in a we go for the sophisticated analysis approach, is very difficult to find out the which therapy is doing better as compared to others. Sometimes it's not that experimental would be always better than the existing one. So sometimes it can be reverse order also, but that's the reason. So unless and until we try to capture the how the data distributions is over there, is very difficult to get the proper or correct answer over there, because whatever we are doing today, that is going to be implemented in the future. So persons are going to be implemented, or prescription is going to be implemented based on future in future based on today's work. So that is very much important to understand the data capture and data distributions. So this is that again the disclaimer. So that we have seen that earlier, that p-value for log-rank test to check whether two groups differ with respect to others or not with the survival analysis. One reason such tests are useful in provide the objective criteria, statistical significance around which is to plan out a study. Now questions come: how many subjects we do need, how long we study to take to complete, and that some extent we understand. And while we are last day we are talking about the sample size calculation, we also mentioned about that. So now things comes that in survival analysis we need to specify the information regarding the censoring mechanism, particular survival distribution in null and alternative hypothesis, that some extent we also covered. Now while you are talking about the survival curve comparison, so that there is a called life table. So that we have seen just the table, like we started with the ST, then MT, ST, or MI, then NI, then QI, then all calculated the probability of table. So these are basically nothing but the preparation of the life table technique. So life table technique helps us to get the survival ST, and it's fixed with particular time point. It's split the entire time point, entire duration of the study point into different span, like 6 months, 12 months, 18 months, like that. And that's why that measurements comes, and that these splitting time points can be considered as in theory part, it can be considered as Li to Lk. So how many parts you are splitting the entire duration observations. So look, while you are talking about the survival curve preparation also, throughout the x-axis also we put different time point. This is basically the we can't observe the inter-study at a glance. So we have to split the inter-study duration into different part, and based on that we are going to make the comparison. So with different part, let's say with the 6 months to 6 to 12 months, 12 to 18 months onwards, the number of patients are died, that is contributed by the defined as a DI. And thereafter another part comes as a loss to follow-up of Li, and withdraw, and loss to follow-up and withdraw from the study. So that is another part we never touched until now. But one thing is that some persons, while you're talking about the typical clinical trial, so we think that some persons may be withdraw from the study. So they are not lost to follow-up. We can't consider them lost to follow-up, but they are withdraw from the study. For that part, the provision is there. Now how to make it? So that's the inter way to go with the reduced sampling methods and calculate the survival analysis. So you can get this the way to calculate the sample, or do the survival analysis by reduced sampling method. So once we are having the reduced sampling methods, the estimations of function of ST, that's I gave it here, only those subjects who are at risk, that I have seen that we, once you are going to calculating the samples table, or you're going to for the ST, then we only concern about the number of people at risk. So those are censored, those should be subtracted from the sample size. Those are withdraw, that is W, and LI. So those are, LI is basically the total number of people, those are lost to follow up, and WI, those are withdraw from the study. Those need to be calculated for all time points separately, and each time point need to be subtracted from there. And definitely we are going to get the final death numbers or counted number, how many are going to die or died or even happened, that by D. So once that is done, then simply we can make the survival function by 1 minus D by N. So that's the reduced sample method says. So it's a basically combinations with their subtractions and additions, that methods. So particular time point, go and ask, see how many people are died, take that value and divide it by how many were at risk. How we are going to get that risk? That N is basically subtracting how many number of lost to follow up and how many were withdraw from the study. That's all. Like Dr. Durga said that if you are having something like 1% are progressed and after that shifted to another inappropriate therapy, and what to do? So in that sense, in your cases, the person is basically, you can say the withdraw. You can, if you think, and you can be with me, or you can also oppose. But if it would not be wrong if the person is withdraw from the study. So in that case, however, sometimes we consider the withdraw and censoring in the similar fashion, but because both are going to be subtracted from the inter-cohort study. But if 3 months later that persons are withdraw from your study, because the persons having so many reasons. One reason is the progressions happened, so they were not relying to the existing therapy, so they move to another therapy. So that's why the withdrawn from that. So that's why the UWI is happening here. So that persons can be subtracted immediately from persons such risks over there. As by default we call it as a censor, but we can subtract it from here in I, and we can come down or bring our sample as in, and that's why it is called reduced sample size, sample methods. So the limitation with this reduced sample method is that it ignores the information about the content LI and WI. It is biased estimate sometimes of the ST, but it is the easiest way to calculate that. Another method is the actuarial methods. Actuarial methods is a survival probability method. It can be produced in a product of the probability. So here, one thing is that here we are just ignoring the time as a constant factor. So time you are not considering. So here directly we are taking the entire number of people and just making the how many died and how many were alive at risk. By that we are going to make the S of T, and survival probability we are going to make it. But actual method says that probability, it's a product probability. So see, here probability is basically estimated by production, simple multiplication of that. What does it mean? It says that particular time point, how many people were probability of survival, that would be conditionally multiplied with this earlier time point, how many were alive. So the question is that, the simple question is that if a person comes, if say how many months I would be alive as a cancer patient, if somebody comes and say how many months I would be alive, so the person, you can give an answer, you will be alive up to 10 months. That can be answered. Another way, but 10 months the person would be alive, it's based on that if the person get alive up to 9 months. So those are alive up to 9 months or beyond 6 months, they are going to be alive up to 10 months. So the condition is very much important. So those are passed to have certain number of months to get alive. They are going to be alive more than that. Correct? So that's kind of probability is always required to be keep it in mind while we say. So sometimes happen that literally people say that okay, you can be alive more than, let's say, more than 10 months, okay, after having your surgery, but after having the surgery, what is the probability of to get alive more than 2 months? If it is a below 20%, below 50%, below 60%, then only makes sense to have go beyond 10 months, right? So every time points, and sometimes the COVID kind of things always occur, some not always occur, sometimes might occur. So in that sense, the probability of getting died makes more important and it's get reduced. So that condition, so time dependent condition is always need to be keep it in mind, and that's why actual method is much more stronger than reduced sample methods. And here we take the multiplication of the conditional probability for earlier time point and make this next time point probability of survival. So these methods provide an estimate for PI separately and then multiply with the estimate together for the estimate of earlier time point. The estimates is basically, look, earlier reduced sample method, we use the D by N. Here we are going for DI by NI, DI by NI. So in case no loss or withdrawals are there, so we are going to take it as a NI as an impact, and thereafter we are going to divide it from DI, and thereafter we are going to make that one. So how it's going to have? It's going to have that multiplications factors. This is going to have the multiplications of the probability. So each time point we are going to make the simple probability of survival, and thereafter we are going to make the multiplications. That's the way it works. And grid formula is there, that is addition to the actual formula, actual methods formula. So I'm not going on that. So to recapitulate, we shall consider the following function in survival. T is a continuous positive random variable. Function of T is the probability density functions. F of T is the cumulative density function. ST is the survival function of the probability of being alive. And thereafter, another thing is come the hazard function. So hazard is very much important, but it's basically comes as an additional impact or product of the survival function's value. And sometimes, many times we call about the hazard function or hazard rate, hazard ratio. These are the byproduct of the survival functions. So now how it happened while you know that you can capture the data in a particular distribution form. The exponential distribution is one of the typical example of the exponential distribution. You can see that while the time passes, the persons are it's become very growing is very rapidly. This is the exponential distributions form. So if we are in a position to capture that, as because most cases as time passes, many people started to die fast. So that's mean the number of people die within 1 month will be less as compared to number of people who will die between 12 to 13 months. Number of people will die between 12 to 13 months will be less as compared to number of people die within 23 to 24 months. So that's mean while time passes, number of people death rate for particular time point keep on increasing. That's in our general normal life also. It's not only the cancer, it's in normal people also, it's get the similar fashion. The persons that in 4 years of age, 5 years of age, 10 years of age, and slowly 50 years, 60 years, 70 years, and after 80, 85 and 90 years, you will say that also remain the similar. So persons die within 4 to 5. If you now forget, because the child mortality now is well controlled, but otherwise that was in another scenario. But if you ignore the child mortality rate is high or not high, it's in a similar fashion. So right now we are in a better position, but still, if you see number of persons die within 5 to 6 years, 6 to 7 years, and slowly, and it gets up to, if you talk about 60 to 61 years, 61 to 62 years, it's keep on increasing rapidly. People are going to die once their age are going from 1 year to another year. So that's it, basically typically a formation of the exponential distributions. And while you're talking about the exponential distribution, so it is better to capture the data with the exponential distribution format if your survival functions or survival distributions coming in that direction. So once you are having that, then making the comparison between the two groups makes more important and makes more robust than without looking the survival comparison, without looking the exponential distributions. So exponential distribution, Weibull distribution that I'm going to say, all these are the parametric distribution format. So basically you are in a position to capture how the distribution is going to happen. Even if you collected the data on the stipulated time point for, let's say, for 1 year, but still you can, if your data is following particular distributions, so we can get some kind of information what going to happen up more than 1 year. That information is having that power is having for the exponent of the, if you can capture the data with a particular distributions form. So this is that if you in terms of the probability of survival, if you talk, because the probability of survival is, if you keep on decreasing, it's a formation of the exponential distributions from left to right, like that it's going to happen. So exponential distribution have some parameter of interest that need to be considered. I'm not going to details, but let's say these are all basically the to deriving the mean value, to deriving the standard deviations value, to deriving the functions value, and ultimately the survival functions for exponential distributions is taken as e to the power minus lambda t. Lambda is basically that mean value we are going to calculate, and t is basically the time. So that's the risk assessment is done for the exponential distributions. So if your data is following exponential distribution, it is nothing but good to apply the parametric distributions and make the comparison rather than going for non-parametric or log rank test, or let's say, or Gehan test, or say like any kind of Kaplan-Meier statistics. I'd say the Kaplan-Meier is typically the non-parametric rather than that one. This is the strongest approach. But one thing that we have to explore the data, we have to give time to analyzing the data. And if you can pick the distribution is following exponential distribution, this is the best approach to apply and get the result, most robust approach. Other formations of the data is there, like gamma distribution. So sometimes, like we have seen that earlier presentation, that survival curves could be in different formations. Sometimes goes up, down, then slowly goes down. So like yellow color. So it started with the steady line and then dropped down. So like it blue, that dark green color, like this one, it started steadily and suddenly dropped down. It started like typical this way, the blue color, or it started with this red color, goes, and thereafter that. All these are the typical survival distributions formations. And these typical formations can also be captured through gamma distributions by twisting these parameters by alpha, D, and P. So these are the simulated distributions I'm showing, but in real life data survival distributions could be like these as well. So if your data is looking these distributions, don't overlook the data by applying by default Kaplan-Meier estimator or non-parametric approaches. You can proceed with the gamma distributions, and gamma distribution as a parametric is going to give you the best result comparison as compared to other, because others don't consider that distribution formation is there. Because once you make the robust inference, even if your data is very low, your study power is very low, still you are going to get the robust estimates value, and that's meaningful value over there. And it's in terms of the patient's care, it makes sense on that. Similarly, gamma distribution also having calculate the mean and variance, and there is some formations, and that's not, I'm going on that. So it's basically the gamma distribution says that the incomplete gamma functions by complete gamma functions, and there is a formation. So again, softwares are there nowadays. You have to test the data distribution is following gamma or exponential or not, and there you can apply it. Weibull is another form most commonly applied where the patients are, these kind of distributions occur when the patients are after having surgery. It's happened that mostly in the cardiac arrest or having the CVD surgery, then immediately after a couple of hours or couple of days, we see that huge amount of people died. So means number of people die within a very small span of time is quite high, and slowly their value is going down. So they get stable. So if your data is following Weibull distribution, if you're doing surgery and you see that in ICU itself, before discharge a patient itself, event occur, relapse occur, or patient die itself, in that sense, Weibull is the best one rather than going for conventional one. Because if again I'm saying, if your sample size is low, you in a positions to capture it is following Weibull distributions, better proceed with the Weibull distributions and get the most different statistical difference by that. Again, it is also having similar fashions to get the mean and variance value calculated, and that's formation. So basically, see, Weibull, gamma, and exponential all are basically calculating the hazard ratios and hazard lambda, and lambda is basically the function of ST and formulation of that I have mentioned here. So lambda t is the cumulative hazard functions, and lambda delta t and lambda t is basically function of t by st. So that functions are used here. So another way is a log normal. So then again we can apply the Lagrange. The same story is there, Lagrange. Gompage may come, another story, another type of distribution. Then again, if you're following that type of, you can apply, and it's having the formation of that generalized gamma distribution, another formations. So you can apply. So these are the noting I'm saying. So this it's a, if you can give more time, you can erase those distributions and apply parametric formations. These are the formations for the gamma and illustrations of that. And finally, all distributions, whatever I mentioned, they are basically going to for the Emily maximum likelihood distribution test. And if maximum likelihood distributions are basically calculate the likelihood of the probability of the persons to being alive or dead, and that is a fundamental way to calculate. So with that note, I would just my intention of all these things is that there are different way to distributions to make the comparison of the statistical test. It is a parametric, it could be a parametric, it could be non-parametric. Safest and easiest, definitely the non-parametric, and nobody can raise any questions on that if you apply the non-parametric, because it is safest, I would say, because blindly you can apply non-parametric, blindly in any data you can apply Kaplan-Meier, you can apply the like table, you can get the results. But if you are want to go your statistical test to be more robust, why it is required? Because sometimes even in small data or large data, we can get the non-parametric Kaplan-Meier and all these stuff, but small data itself, it is quite challenging to accept and get the publications to be done in a reputed journal, because straightforward able to throw that data because it's a study sample size is quite low. Now, if your study sample size is low because you put your all efforts and you are not in a position to capture more patients, because I know in Indian setup there is a very loss to follow up. Is there compliance issue? Is there data capturing methods is not so strong? So that's kind of scenario is always there. But still, if you can, whatever the best data you are having, pure data you are having, in that, if you can apply more statistical way to look at the data, find out the distribution test, and proceed for that parametric way, that is the better, strongest approach than just go and throw it because it is a non-parametric and you are not going to get any results. So that's not advisable. So that was my point, or I wanted to add this point to note here. So, and softwares are available. You can go for parametric, you can check for different distributions. It is not always that you have to test the data distribution. You can blindly apply all these parametric model, like I mentioned, exponential, Weibull, gamma, and best methods you can adopt and you can get result on it. So with that note, I would end here my third presentations, and